Welcome. Now that we have a clear understanding of how to use mathematical equations to describe the dynamics of an infection of a virus inside a typical host, we can modify or adjust these mathematical expressions to account for therapy. Specifically, when an infected patient is given some type of drug or drugs, um, what occurs here, unlike for infections due to bacteria, the virus cannot really be clear or eliminated by the direct action of drugs. Antiviral drugs, which would be the analogous to antibiotics, are drugs that are, instead of targeting or instead of intending to kill virus or clear virus, these are drugs that will interfere with the life cycle of a virus. And so we are going to review how the mathematical expressions in the model can be modified to simulate the so-called treatment schedules. And one of the first schedules that we discussed, so one of the first types of drug therapy schedules that we discussed has to do with the reverse transcriptase, the inhibition of the process called reverse transcriptase. So let's now look at the equations. These are the original equations describing an infection due to virus. As you may remember, there are three populations here: the uninfected target cells, the infected target cells, and the population of virus. The treatment that we're going to review right now has to do with the inhibition of this is typically used the acronym RT, the reverse transcriptase process is going to be perturbed, or it's going to be changed by action of the drug. The drug is intending to interfere with this. So in other words, the drug will be blocking infection um, by means of that inhibition of the reverse transcriptase. And that directly reflects on having an effect on the interactions between between virus and infected cells. Okay. Specifically, we would say that, or specifically, we would note that in the sense um, in which the inhibition is perfectly carried out, okay, in a perfect scenario, we would have that this term would be 0. Okay, if that is as perfect as it can be, then the interactions um, between virus and cells that are uninfected, those interactions disappear. That would be the most ideal scenario in which the inhibition is carried out in under excellent conditions. And so that would mean that the new model would reduce to this. And as you can see, the interactions between virus and uninfected cells have disappeared. And in a way, these state variables now, at least the first two state variables now, are independent of each other. This word of independent is something that you would say in these mathematical terms. They're decoupled. These equations are decoupled. Okay, and in this current state, you can see how the population of infected cells is basically destined to, this is linear in I, right? And you can right away tell that this would have solution that looks like an exponential, that looks like this, e to the minus a t. That's what I of t is more or less behaving like. This is pending to some initial conditions that it's telling you that the population of infected cells with this model would be subject to exponential decay. Okay, Now, you kind of saw a preview there. Um, what happens if we're in the scenario in which the inhibition is not necessarily perfect, okay? In which the inhibition is subject to a level of effectiveness. Now, that level of effectiveness can be expressed in the equations by this type of reduction on the interaction parameter. So basically, you're arguing that you have the interaction parameter beta, and this is changing from beta into that number multiplied by a term that looks like 1 minus um, a letter, a Greek letter, eta there, right? So if we think of eta being a number, say, between 0 and 1, okay, then 1 minus eta is also a number between 0 and 1. And this expression here denotes a reduction on the interaction term between virus and uninfected cells. Okay, and so this is one form of expressing or modeling um, the treatment when that treatment is targeted at interfering with running some interference with the way in which virus and uninfected cells are interacting with one another. So the model with treatment by means of inhibition of reverse transcriptase looks in this way. These equations are very consistent with the equations we had for a simple model of virus dynamics, but now we have this additional parameter that denotes the effectiveness of treatment. So as we had already pointed out, when this parameter is the case we discussed, and we wrote equations there for the scenario in which that parameter is equal to 1. So when eta equals 1, that means that the combined new interaction term, 1 minus eta quantity, 1 minus eta times beta, when eta is 1, that makes that whole thing become 0. Okay, and so we would say that when eta is 1, the inhibition is 100% effective. However, when eta takes the other extreme value of 0, there is no inhibition. That means um, there is no treatment. So let's now review some numerical simulations of this model and their different types of treatment schedules. So here we have a numerical solution of the mathematical model, and just for purposes of verification, we solve the equations with that effectiveness of treatment parameter equal to 0. And we're using the parameter values we had employed before for the scenario in which we had a stable endemic equilibrium. So with eta equals 0, this means there is no treatment, and this gives us a verification that the numerical solutions are exactly what we expect. They're exactly, they look very similar to those solutions we had obtained on a model without ERA, without treatment. Okay, so this is for simple purposes of verification. You want to observe here, or acknowledge that this population in red is the population of uninfected cells. These three populations coexist with each other. However, the number of the amount of virus for these values we're using here for purposes of illustration, the amount of virus outnumber or outcompetes the infected cells and the amount of uninfected cells. Now, what we see when we consider the other extreme scenario where daily treatment is actually as effective as treatment can be, with eta equals 1, 100% effectiveness, this causes the system to basically be perturbed, and even though the system was already settled into a stable equilibrium point that we called endemic equilibrium, by applying treatment in full force, in that exaggerated way, we cause the system to settle on another equilibrium point that we know as the disease-free, the scenario in which um, the population is completely free of infection. Okay, so here both curves for the state variables infected cells and viral load are in quite a march, quite a walk headed to values that are 10 to the minus 1, 10 to the minus 4, and higher orders approaching zero. This means basically that the system, that with treatment this effective, then it's possible to eradicate virus, at least in the way in which the equations were represented.